All right, our next lesson in this unit on probability is titled Theoretical Probability. This is digit 17.4. In your table of contents, add the title, Theoretical Probability, and then on the next clean sheet of notebook paper, add the title, Theoretical Probability, and then our essential question for today is how can I tell the difference between experimental and theoretical probability? Hit pause and set up your table of contents and your notes. When you're ready to move on, hit play. All right, how do I determine the theoretical probability? You don't need to copy this entire thing. I do want you to copy this right here and the little formula, okay? How do I determine the theoretical probability? Sometimes you can find the probability of an event through reasoning about the outcomes in the sample space. A probability found this way is a theoretical probability. I guess we do need that because that's the definition. Sorry, y'all, I was trying to make it less, but oops. And you can underline this right here. This is your term. Okay? So it says your reasoning. This is the key thing here with theoretical probability. The difference between the theoretical probability from the experimental probability that we did yesterday, we're not actually rolling a number cube, flipping a coin, spinning a spinner, doing the experiment. We're thinking about it through reasoning. Before we did the little activity where we flipped the coins, we thought about what would we expect the probability be of flipping a heads, and we said 1 out of 2 because there's one side that is heads out of 2 possible sides. That was finding the theoretical probability. Okay, the experimental probability was when we actually did the experiment of flipping the coin however many times and writing that as a ratio. When all outcomes of an action are equally likely, we can use the theoretical probability formula, which is this. Again, remember this probability notation where we have P and then whatever the event that we're finding the probability of is written in the parentheses. We're going to put the number of favorable outcomes over the number of possible outcomes. And when we say favorable outcomes, that just means outcomes in the sample space that satisfy the event. So like if I said rolling an even number, okay, we would think about how many sides on a number cube are even. That would be 2, 4, or 6. So that would be 3 of the sides. Okay, so that's what favorable outcomes means. Hit pause if you haven't finished copying this down. When you're ready to move on, hit play. Okay, let's try this example. They already have it worked out, so just read through it with me. It says, here are 2 views of the same number cube showing its 6 faces. Find the theoretical probability of rolling a 0. Well, we see of its 6 faces, we see one side right here that has a 0, and then another one that has a 0. From the sample space, these are the 6 sides right here on the number cube. How many of those do we see are a 0? There are 2 sides that have a 0. Would we put a 0 right here? No, we don't put a 0 because it's the probability of 0. We put the number of sides that have a 0, which is 2. So the probability would be 2 out of, there's 1, 2, 3, 4, 5, 6 sides total. 2 out of 6 we can simplify to be 1 over 3. All right, let's try this one. It says, suppose you choose a button at random from this bag of buttons. What's the probability of choosing a blue button? So I'm going to say P, why is this not writing? Hello. Go ahead and be counting how many blue buttons you see, and let's see if this will work now. Yep. So we're finding the probability of getting a blue. I do want you to write this down. We'll call this example 1. Okay. How many blue buttons do we see? 1, 2, 3, 4, 5, 6. Out of how many total possible buttons could I pick from? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 6 out of 12. Can I simplify? Yes, I can simplify. My board will ever write. There we go. That would be 1/2. So I have a 1 out of 2 chance of picking a blue button. Then the second part says probability of choosing a 2-hole button. Well, I've put all these dots on it, so I'm going to erase this so I can see how many holes. Okay. How many of these buttons have 2 holes? It looks like this one and this one have 2 holes. I don't see any more that have 2 holes. So we're just going to say 2 out would be the probability of picking a 2-hole button, which I can simplify to be 1 out of 6. Okay. Next example, looking at a spinner. The spinner is divided into 2 unequal sectors. The outcome for red and blue are not equally likely. Explain how you can use the theoretical probability formula to find the probability of spinning red. Well, what is the theoretical probability of spinning red? It's the number of favorable outcomes out of the total number of outcomes. If I divided this spinner into 4 equal sections, remember it has to be out of an equal number of possible outcomes, how many of those equal sections are red? 3. Out of how many total sections are there? 4. So the favorable outcomes, the probability of spinning red, how many are red? We said 3. Out of how many total sections? 4. So if you don't have equal sections, look at what you can do to get equal sections so that you can then find the theoretical probability. All right, boy or girl. Our sample space, it's either a boy or it's a girl. If the outcomes boy and girl are equally likely, then the probability of getting a boy would be 1 out of 2, 50%. All right, I do want you to copy this down. Compare and contrast. Copy this into your notes. Hit pause real quick. Copy, then we'll move on. Theoretical probability is based on reasoning about equally likely outcomes in a sample space, and it compares the number of favorable outcomes to the number of possible outcomes. Whereas with experimental probability, we were basing that on observing outcomes of repeated trials of an action. So we're actually flipping a coin, spinning a spinner, rolling a number cube. We're actually doing that action, each of those trials. And we compare the number of times the event occurs to the total number of trials. So make sure you see the difference here between experimental and theoretical probability. All right, let's try this together. Just put ABC, you don't have to copy the thing, and then you can say on your own experimental or theoretical. For A, a soccer player took 12 shots on a goal and scored once. So the probability of a soccer player scoring on a shot is 1 out of 12. Was that based on experimental or theoretical probability? When the soccer player actually took the 12 shots on the goal, that was actually doing the experiments. That would be experimental probability. All right, you roll a standard number cube 50 times and get 3 8s. Or 8 threes, I can't read straight. 8 threes. So the probability of getting a 3 is 8 out of 50. They're basing that on 50 times you roll and getting 8 threes. That is also experimental probability because you are actually rolling the number cube 50 times. Okay? C, you choose one tulip at random from the vase. So how many tulips do we see that are red? We see 1, 2, 3, 4. Wow, that's right, 4, 5. And then how many total tulips are in there? 12. This would be theoretical, okay? Because we don't actually have data of, I picked the tulip 20 times, and of the 20 times I got a red tulip 5 times. This is just basing it on what do we see right here. What are the number of total possible outcomes? 12. How many of those are red? 5. 5 out of 12 would be the theoretical probability. All right, hit pause and try this one on your own. Pick which of the probabilities are experimental. All right, for the first one, is this experimental? Yes, because the eye doctor has examined 10 people and found 4 colorblind. That he actually did 4 out of 10 were colorblind. That is an experimental probability. The second option is this experimental. They choose a student at random from a class of 13 boys and 12 girls. No, we see this is theoretical probability because it's the number of boys in the class, 13 out of the total number of possible outcomes. That's theoretical probability, not experimental. And then the third one, you check 6 boxes of cereal and find that 1 box has a prize at the bottom. We actually did the checking. We found 6 boxes. We had 1 with a prize. That would also be experimental. So when you're doing the action, that's experimental. When you're just thinking about the number of possible ways you could get that probability, that's theoretical. All right, last thing, one more definition, simulation. A simulation of a real-world situation is a model used to find probabilities. Copy that definition down. Simulation of a real-world situation is a model used to find probabilities. So here we have some different examples of simulations. So if we wanted a situation with two equally likely outcomes, one simulation that we could use would be tossing a coin, because how many equally likely outcomes does that offer? Two, either heads or tails. If I wanted a situation that had 6 equally likely outcomes, what simulation could I use? I could roll a number cube, because I know there's 6 sides on the number cube. If I wanted 8 equally likely outcomes in a situation, a simulation I could do is I could draw a spinner that has 8 equal sections, and that would be my simulation there. Okay, so for simulations, you're figuring out which object can I spin or flip or roll that's going to give me however many outcomes I'm searching for. All right, so if we have a class that has the same number of boys as girls, each day the teacher chooses one student at random to take attendance. The school year has 180 days. How many days would you expect the teacher to choose a boy? Well, if there's 180 days, and there's an equal number of boys and girls, I would say that there is a 1/2 probability of a boy taking attendance and then a 1/2 probability of a girl taking attendance. So what is half of the 180 days? Half of the 180 days, I would expect 90 days for attendance to be taken by a boy. The other 90 would be by a girl. All right, if we wanted to use the probability tool to simulate the situation, we would use a coin toss, because we're looking for something that has 2 possible outcomes, 2 possible equally likely outcomes. And they made this little coin. I'm not actually going to flip it, but you could flip it. Would we expect it to get exactly 90? Maybe not with a coin toss, but we would expect to be close. Okay, so that would be the difference between theoretical and experimental probability. Last example. In one family, a child's chore for the day is chosen at random. The table shows the results of using a spinner to simulate 99 days of chores. For which chore is the number given by the simulation closest to the predicted theoretical probability? Well, if we have 99 days of chores, what do we see? Each of these possible chores is, what's the section? Each of those is going to be 1/3. So 1/3 of the days we would get clear the table. 1/3 of the days we would get set the table. 1/3 of the days we would get wash the dishes. What is 1/3 of 99? 1/3 of 99, if I divided it by 3, I would expect to have about 33 days clearing the table, about 33 days setting the table, and about 33 days washing the dishes. So which of these chore simulations is closest to what we would expect? Which of those is the closest? The blue is the closest, because what do we have right here? 32. That is by far the closest to the theoretical probability. So in this table, we have the experimental probability, where they actually spun the spinner 99 times and put the data there. Over here, we found the theoretical probability of 33 for each of the equal sections. Blue was the closest to our theoretical probability. All right, at this point, you should be ready to do the digits assignment 17.4, and then you also have those Unit 16 IXL skills to work on. If you have questions, please feel free to ask me.